Okay, welcome everyone. We are Group 52. My name is Joseph. And we are All In. That is our team name. Okay, so here you can see a beautifully designed prototype we have. And yeah, so let's jump right into the needs identification. So we kind of found that wheelchair users are engaged in tasks every day that often limit their use of their hands. Oh man, it's kind of hard to okay. And basically, this kind of like leads to like hand movement kind of limitations. Also, through repetition of like wheelchair movement, it's very easy to kind of have some injuries related to this as well. And for those playing sports with wheelchairs, those playing more than one time a week, or who had like more sports like with these chairs, had a 75% occurrence in rotator cuff tears compared to those who didn't, with like 36%. And this created a big barrier to participation for a lot of users after the chairs. And then anecdotally, we met someone named Adri Batra from Laurier, who enjoys street hockey as a hobby, but finds his arms frequently get fatigued because of like the use of just one hand. And this can create like a steep learning curve for those that play sports in wheelchairs. And also another friend we met, Brody, also found physical limitations that not only affect performance, but also can like discourage like play with like non-impaired individuals, and this can kind of like widen the inclusion gap associated with that. So this leads to our needs statement that there needs to be a hands-free mobility device for wheelchair sports, prevent overuse injuries, and reduce the learning curve, make recreational sports more accessible for everyone. So our problem definition is a hands-free propelling and steering while handling a hands-free device, so that people can like use their hands while playing a sport. And we are working with Capacity, which is an initiative on campus to increase accessibility. And we're going to work with them to create a chair that we could potentially use for drop-in gameplay on campus, so potentially at SIF or like PAC or something like that. And for our problem definition, we're going to focus on basketball to limit the variables that we need to consider. And yeah, that'll be indoors, and Amir will take it from there.
So in terms of user requirements, they're non-measurable, they're big. There has been movement since last time. Essentially, you should be able to operate the wheelchair without using your hands. The operation shouldn't interfere with gameplay. It's simple and intuitive, and can accommodate a variety of or varying level of disability. However, anything below the diaphragm, so that's 1 to 2 level disability, you can't actually use the wheelchair. There's no way to lean forward, backwards, or back, left and right. So that's kind of the limits, but otherwise, anything else works. And lastly, also just safety. So yeah, make sure it's safe for yourself and those around you. So in terms of your requirements, you're basically looking at what happens to the acceleration velocity during time for the typical basketball wheelchair player, and also the operating time, which is how long it takes for a game of basketball to happen, and also weight capacity. And yeah. So for critical geometry, a big part of this is looking at the friction between the Omni wheels and the sphere. So we have 3 Omni wheels, and just taking the cross section, you can see that as you place the Omni wheel closer to the equator of the sphere, you increase your normal force, which means greater friction occurring between them, which is used to transmit work. And That's set to 60 degrees because we're limited by the load capacity of each specific Omni wheel, which is 7 kilograms. And you look at the contact length of the Omni wheel, you get your beta angle, which is essentially just a twist on the Omni wheel. At 0, you have the best kind of best kind of friction cone for just translating. At 42 degrees, they sit on mutually orthogonal planes, which means that moving just one wheel, doesn't backdrive the other one, so you get a very efficient. It becomes more efficient to actually drive the wheels. We set it to 30 degrees just to also allow for spinning, to make the mutually orthogonal thing, so it's more efficient, and then also, for translation. Next is just specking the thing, the transmission itself. So we just look at planar models, ZX, ZY, to look at, and some numerical methods to look at what torques we're going to require for all directions of motion, which we map from the sphere to the wheels themselves. That gives you the requirements you load, and then we essentially choose a motor, and those are continuous specs. So there's a little bit of overhead as well, and we put a 1-to-4 reduction. For mechanical design, we're using spur gears because they're simple, cheap, durable, and they're most importantly back drivable. All the bearings, the shaft, everything else, including the segmented chassis, have all been spec for the weight capacity. And then it's connected together to these gussets over here, where you take these 30 sections. And then the safety segment is essentially just make sure that you don't tilt more than 15 degrees, and you don't fall over or like you get ejected off the chair if you crash into something. And then also we have ball arresters, which are spring loaded to keep the platform in steady contact with the ball itself. The chairs are just going to be adapted from the manual basketball wheelchair with a plate with the thing on top. Okay. Oh, lastly, if the friction isn't enough between the ball and the Omni wheels, which I don't think it will be, we're going to coat the wheel itself in SBR, or synthetic rubber, using the pattern that you see on a soccer ball normally.
Alright, so for the electrical system, it's composed of 5 subsystems: power system, motor control, fan network, MCU, and IMU. So for the power system, it consists of batteries, fuses, relays, voltmeter, monitor, and e-stop. And that's used to control the motors, to power the motors and to power the low voltage electronics. So for the motor control, we're using O-Drive S1 and M8325 motors, which is also O-Drive, which comes with built-in encoders. For the CAN network, that's going to be the backbone of our communication, and we're going to be using that because it's reliable under load and noise. And for our MC selection, we chose the TC 4.1, and that's because of its low latency, or low latency, and it's going to be used for our controls and algorithms. And finally, for our IMU, we selected the BNO86 sensor, and it's going to be used with redundancy, so we're going to have 2 of them. And you can see sort of these components together, starting with the TNC in the middle. That's control, that gets into from our IMU, which gets fed into the control software, and then basically through the CAN network, it's going to be controlling the motors through the motor controllers, which provides 2 views of it. So here you can see the component sort of diagram, system architecture, where we just had some electrical system design choices made, and these include having the LiPo batteries arranged in 2 series pairs, which enables fast swapping, modular replacement, and stable hot current output. And we also, for our safety system, have relay recharge circuitry, fuses, and e-stop. And as I said before, sensor redundancy, we have 2 IMUs, one for a remote sensor, and then the other for fault detection. So here you can see sort of the operating time calculations we have. all in all, it's about 7.56 minutes, maximum, rating, so like 85%, motor efficiency, max torque is 3.3 newton meters. But in real gameplay, it might be about 10 to 13 minutes.
Okay, so now I'm gonna be going over the wiring, testing, and like future plans for our electrical system. So, like you mentioned, we are gonna be using like canvas for our motor controller. And at first we are gonna be like visually basically testing like each and every single motor controller. So, in order to we have this TG microcontroller which will be connected to CAN transceiver, which will basically make like a CAN packet and send it to the motor controller with the address and the actual data. We also did some testing with UR, like last weekend. You can have a look at that check over here. But the problem with like UR is you can only control like one motor with using UR. But because we have three motors, or even though like UR is pretty fast, lets you fall. So that's a safety mechanism we are using. It won't allow the board to go more than 15 degrees in case there's a slip. So essentially, we know that depending on the direction that we're going and the user's lead, which is the IQ feedback, we know exactly how the motors or the wheels should be moving. So if they do happen to slip, that means there's no torque being directed. So we can detect that quite easily, just shut down the system.
What's the ball made of? Where are you guys getting?
It's actually a walking globe, so you can already walk on the thing, so it has a high enough moment of inertia, and big enough to walk on it, so we figured that would be good. And also it has to be rigid and as spherical as a sphere can get, so something like a soccer ball or like a yoga ball.
Even not hearing you, so what's the most difficult part of the project?
I mean, definitely like calculating the controls. So yeah, we are still like kind of working on it. We have the calculations. Yeah, you mentioned it, it's basically like balancing the ball, like keeping the top, like basically like balancing the ball. I think spinning is actually going to be most difficult. So how am I going to turn? Because that input you can't use sleep controls.
If you guys have tried riding like the hoverboards before, the hardest thing about it is getting on. How does the user mount this?
So the safety segment right there allows 50 degrees, so you just essentially tilt it, get on, and you can it's also like something that has to do with the user. You know, it's like riding a bike, learning how to ride a bike, if that makes sense. Or learning how to ride a bike.
How like tall is this wheelchair compared to like the standard like competition basketball wheelchairs?
So from base